So today I'm going to talk about this K-stability and various things around it. I try to give you the general picture and do some examples too, so that you get a feeling about this stuff. And if you're an expert, just bear with me. There will be some news for you too. So what is this K-stability thing? I'm obviously not going to tell you just yet, but it's a good thing invented to detect existence of Kähler-Einstein matrix. On Fano manifolds initially, but it's more general than that. So for today's talk, every time I talk about an algebraic variety X, you should safely assume this is Fano. It's a smooth, and it's of dimension n. Occasionally, I change some of these, but otherwise, this is the assumption. Right? So there will be moments where this is not a Fano, for example. Now, what is the story? So given X, you can attach two invariants. To your variety. The first one is alpha X, or log canonical or LCT, log canonical threshold of X. I'm not going to define it yet. If you want me to do it later, I will do, or you could just Google it. Right? If you have not worked with it, just think of it as something that measures singularities of hypersurfaces inside your variety. And if you have worked with it, just follow me. And delta X, known as, this is also called the alpha invariant. And this one is the delta invariant. And known as the stability threshold. And these two will be the main players today. I will define delta in a few minutes, but for now, just these are the two things that are useful for us. So definition, say K as above is X as above is K stable if this delta X is bigger than 0. So complete garbage, bigger than 1. Good. So the story is that this K-stability or semi-stability can be measured by this delta invariant. So the whole point is about computing or estimating this delta invariant. And that's the main topic of the talk today. Cool. Now, here's the question, as I said, given a Fano manifold X or a Fano variety F and X, can you detect K-stability or K-semi-stability? So there are three main tools. And I would say before 2020, before is an E. Anyway, so this is before 2020, almost before 2020. I'll tell you exactly what's happening. So the first one is the most useful one, the most famous one is the Tian Criteria that says if alpha of X is at most n over n plus 1, where n was the dimension, then you have K semi-stability. And later on, it was improved by Fujita and Odaka and Sano. And it says, if you assume smoothness, plus n is at least 2 or strict. So you drop the smoothness and assume that alpha is at least is strictly bigger than 1. Then you get K-stability. So this equality just goes away. The next one was introduced more recently by Ziquan and Zhuang, my collaborator. So X is less abbreviation, is birationally super rigid. So you assume X is birationally super rigid, and you assume that this alpha X is at least a half. Then you get K-stability. And the proof is actually very cute. I'm not going to show you, but it's really nice. And then there is the last one, which has a lot of names, so because this is just a long story of things happening. And the last piece of the puzzle was put in by Ziquan Zhuang again, but this is after 22. It is in 22, so that's the only part that was done in 22. But it uses the ideas of our paper that the content of this talk today, at least parts of the talk today. So you assume. So first thing is that if something is K semi-stable, then automorphism has to be reductive. This is known. Now you assume your automorphism group is reductive, then delta, if the delta invariant with respect to a divisor E is positive for any invariant divisor over X, then you get polystability. So I didn't define polystability, but so stability implies polystability. This is, and I can safely work with stability. The beauty of this one is that it says you don't have to do this computation for all divisors. You do your computations for invariant divisors. So larger your group, more powerful this is. Now weaknesses of these three methods. So here, if for example index the index of your Fano, which I define later on, if it's bigger than 1, then it's not going to work because alpha is roughly 1 over X, roughly. So that's not going to work. It just works for particular cases. And also in those particular cases is difficult to compute or estimate. For example, if you have complete intersection Fano varieties in Pn of index 1, where this is useful, but you cannot compute it if codimension is at least 2. So that becomes difficult. So it is useful, but it doesn't work that well. This one is really nice, but it's too restrictive. Binational superrigidity is really strong condition, and that alpha at least a half is probably redundant. And this is obviously. I mean, the weakness here is obvious. If automorphism is small, there's not much we can do. And there's a hidden tool, if you like. That we know K semi-stability is open in the moduli. So you take your X, you deform it to something special. With lots of symmetries. Then you check that X naught is K semi-stable, and then from this you conclude that the general X is K semi-stable. This is what Vanya was talking about the other day. So you do this degeneration and you use one of these three things, usually the last one plus the first one, and you're done. Right. But this is useful, it's really good, it's powerful, but it just tells you something for the general member, and it doesn't tell you what the general condition is. So if I give you X, you still don't know what to do. You don't know what the answer is. Cool. So one key example that I like to work on for a while today is smooth hypersurface in Pn plus 1. So I want to keep the dimension n, and the degree is n. So this is degree of your hypersurface. This is a notation I will use throughout the talk. So in this case, we know, for example, that X is not, just to make sure this is not an assumption, is not birationally even rigid. You have a pencil of one dimension lower Fano Xn in Pn. It's easy to construct. Alpha is half, so that's not going to work. And automorphism is fine. A general one has trivial automorphism. There's none. So none of those three is going to work here. And the only case known I should say is cubic threefold, or K-stable by the work of Liu and Xu in 2019. It is published already. Good. By the way, every time I say a method, I mean algebraic method. So they use a non-algebraic method. It's an analytic method. And we can talk about it if you're interested later. Now, first theorem I would like to tell you. So I had it in the first chalkboard. I wrote AZ20 and AZ21. So there are two papers we wrote with Ziquan. I call them AZ20 and AZ21. 20 and 21 refer to the year 2020, 2021. You can find them on the archive. So in the first one, we proved that if X is Xn in Pn plus 1 smooth, n is at least 3, then you have K-stability. So this is settled completely for this sort of this index 2 hypersurfaces. And how do we do this? It's based on a new method. We call it compatible divisors. And so the main bulk of the talk today is talking about these compatible divisors and why they're useful in this topic. Good. So what was this delta X, the stability threshold? I'm going to define it. So it was introduced by Fujita and Odaka a couple of years ago. Suppose M is large enough, a positive number, integer, and M basis type Q divisor is, do I have room for this? How would you do? The divisor D of this form. So you take the sum of divisors defined locally by SIs. So, and your sum runs from 1 to a number. You divide by this number. So M is there, and then you take this average of these guys, and you assume these are Q equivalent to for anti-canonical divisor. And these numbers and SI is what they are. So you take the linear system 4 minus MKX, and you assume S1 to SNM form a basis. vector space. So it's very clear. You just take a basis for this vector space, and you take the divisor defined by this. You take the average. And obviously NM is just H0. Right, so this is how you define an M basis type Q divisor. And using this, you define delta M of X to be the infimum of the log canonical threshold of the X with respect to this divisor D for all D being M basis type divisor as above. So this infimum runs over your choice of divisor. So you have to calculate it for all such divisors, right? For each M. And then finally, delta X is defined to be the limit of delta M as M goes to infinity. The truth is that it was initially defined to be the soup and the lim soup, but later it was proved by Johnson and Johnson that this is a limit. So what is really measuring the log canonical threshold of the, if you like, the most singular M basis type divisor. So you have a set of M basis type divisors. This is just measuring the log canonical threshold of the most singular such divisor. You could also define it locally at any point X, which do I do it? It's a proper board. I can just mess up like the normal teacher. So you could define delta X to be the same as above. So delta equals X, and you take it to be similarly infimum of all those things. But you're calculating log canonical threshold at that point. Right? And obviously delta X is the limit of delta X M as M goes to infinity. And you can see that this is just infimum of delta X. So when it comes to computation, you can just do it at your points. Take the infimum. Good. Any questions so far? No, good. Maybe. Good. So this is, as I said, this is the definition. So you take this sort of M basis type divisor. So you take a big multiple of your minus K. You look at the divisors coming from the basis of this vector space. You take the average and you calculate the log canonical threshold. So you're looking at the most singular such things. And obviously, there are infinitely many of such things, so it's not an easy computation to do. So you almost never manage to complete it. You can estimate that. That's why things were difficult in the past. What we did is kind of a simple idea. So we introduce this notion of compatible divisor. So you start with a divisor E over X. So it's either a divisor in your variety or it's on some blow-up of X. So it fits some model of X off. And then you say an M basis type divisor D, which I write again as M and M sum of its SIs is compatible with E. So you fix your divisor E. You say an M basis type divisor E is compatible with E if for any positive integer I take, the filtration, which is natural, so I define this filtration on my vector space as the set of sections in here such that the order of vanishing of S along E is at least J. Right. So I can do this easily, and then the compatibility says that such filtration is spanned. So for each J, each part of your filtration is spanned by some SI. So the basis of your vector space that you use to define D is going to be compatible with this filtration that comes from the order of vanishing along E. Right. So let me make a remark before I tell you the main thing. So D is the largest vanishing order along E if and only if it is compatible with E. Right. So this is just the idea behind this compatibility. And if you stare enough at the definition, this should just pop up. Now, what is the idea here? So again, we said for computing or estimating delta X, the stability threshold, you need to consider all these M basis type divisors. Right. The point here is that to compute delta X or even or also delta X, the little one, it is enough to consider basis type divisors that are compatible with E. So you fix an E, any divisor you like, right? And this is true. So the notation we use is right, any X. So this is delta that respects that filtration. So whether globally or locally, this is true. Now again, so you have infinitely many things to consider. Now we're saying, okay, look, you don't have to look at all of them. Fix any divisor you like. Any divisor you like. This should give you the point. This should be enough to compute delta X. But the truth is you can almost never compute it, so it would be good enough to estimate it for you. Why is this true? So I'm not going to give you a full proof. I'll give you the sketch of the idea. So assume delta is actually computed by a divisor E prime over X. Right. So those experts know that there is a different way of defining delta with respect to divisors over your variety. Vanier defined this a few days ago. But anyway, so suppose this is true, which is not known to be true. I'll come back to this in a second. So assume you have a divisor E prime that computes delta. the idea is that asymptotically, delta M is going to be now the log canonical threshold of X and D for any M basis type divisor compatible with E prime. Now this follows from the definition, right? That is the main idea behind it. So as I said, D is going to maximize singularity. D is the one that maximizes singularities of such divisors along E prime. Good. Now choose D compatible with both E and E prime. Right. So the idea is that you have two filtrations. If you like, FE and FE prime. And linear algebra tells you that there is a basis compatible with both E and E prime. So this is your new D, right? So the idea is that you have a filtration coming from E, you have a filtration coming from the E prime, which is the divisor that computes delta. If you look at these two filtrations, it's just linear algebra. So you can find basis that is compatible with both of them. This you can even give it as exercise to your linear algebra students. And that basically completes the proof, because now you have found a divisor that is compatible with both of them, and the number that gives you should be the same. So you have it done. End of the story. Now, what I'm hiding is that if delta doesn't have to be completed by divisor, in general, it's completed by evaluation, but that doesn't change anything. Given evaluation, you have a filtration. So the same story. Cool. Any questions on this? I show you an example of how this can be used. Several examples, but one of them with more details in a second. So, example. I'm going to work with simple P, and everyone knows this is K polystable. If you did complex geometry, if you read the book of Loughborough, for example, he proves it with nothing, so with no algebra. Fix a point X in Pn, and now I'm going to make a choice of a divisor. So I let this E to be a hyperplane, as you guess. Right. So, for example, I let, if you like, this to be X not equals 0. Now, what is a basis type divisor? The basis of H naught of O of M. Now this is I want it to be compatible with H. So such basis consists of the following. So I want to, so at each level, I want to maximize the possible vanishing along E at each step. Right? So I obviously have this. Right? This has the largest vanishing order along E. And then what else do I take? I take one degree lower, X1, and I get all the way to right, to Xn. And similarly, you just continue, right? So the next step, you get m minus 2, x1, x2, and then you just keep going down, right? So this is it's going to define for you the basis type divisor. Now, what do I want to say? So this divisor D is going to be, again, I'm interested in the asymptotic behavior, right? Asymptotically, as m goes up, it corresponds to, so I can write it, as a times h. So as you see, this h is going to come out throughout. And don't forget, I'm taking average. So I'm dividing by this m and the number of the elements in the basis. So plus something else, gamma, that doesn't have h in it at all. So those who are familiar with things in the subject, so this a is just this s of minus k. It's that integral. Okay, and in here you can calculate that this is just 1. So what is the idea? The idea is that we want to know if D is log canonical or not. Right. I.e., you want to see if delta is bigger than 1 or not. So now you have so bidimensional geometers know this is a perfect recipe for inversion of adjunction. So inversion of adjunction tells you that D is log canonical if and only if gamma restriction to H is log canonical. And this is the key. Right? This is the key in the induction that you saw in the title, and this is the idea. So I start from a variety, and then I do this small trick to go 1 dimension lower to something else. And in here, for example, you know that D is minus K, Q linearly equivalent to minus K, and that implies gamma restriction to H is nothing but that, which we know is not canonical. So therefore, X and D is not canonical, and eventually that gives you P and X. Good. So the point is this: the induction step is easy to understand. The ideal from the previous page is easy to understand. What is crucial here is this choice of E that I make. So I said you can take make any choice you like, but you can see that in doing so you may mess up with this gamma. For example, if you take I don't know, E to be O of 2, then you basically at each step you're making things much more complicated, more singular. So when you go down, it's harder to analyze the singularity. So this choice is still part you need to know how to do. So good. And one remark is that this concentration of the singularities of D around H implies that this gamma that you obtain here, that you use for induction, so the concentration of singularities around D imply that the degree of gamma is very small. Right? That's why it becomes useful when you go down. And that's because I made the choice of E to contain my point X. So for some other cases, which I don't talk about today, you may make a different choice. So you may take E to be not to contain X. But anyway, so it's not tough. Cool. Maybe I don't talk about admissible flags. I'll just mention it quickly. So, so this came up. This is in the title of the paper, in fact. So this is a work of Lazarsfeld and Mustad. I'm not going to tell you much about it, but we define this compatibility not with respect to just the filtration that I talked about. We define it with respect to a filtration that comes from an admissible flag. But the idea is exactly what you saw in the previous example. You take Pn, you make a clever choice, you go one dimension down, and there we got it for free, but you could still continue. You make a clever choice, you go one dimension down, you construct a flag, and that flag gives you the filtration, and you have the rest of the story. And you can do inversion of adjunction plus this induction thing, and sort out anything you like. And as I said several times, this choice of E is the crucial thing here. Anyway, so one theorem that I'd like to show you at least, so again, comes from AZ20. I'm still in the previous year. So as before, X is Fano, and dimension is N, and take L to be a line bundle on X with minus K X RL. I want to assume that Ln, the volume of L, is N plus 1 over R, is at most N plus 1 over R, such that for any X I take in my variety, there exists H1 to Hn minus 1 in this linear system L, such that X is contained in this intersection, which is a complete intersection, giving you a curve. In fact, I want it to be integral. And if all these conditions are satisfied, so again, it looks scary, but it's not a complicated thing. So I take a line bundle. Obviously, it's going to tell me, but I'm not assuming Picard number is 1, but you know, so you assume it's a multiple of it is minus K, with this condition that the volume of L is bounded by N plus 1 over R, and you have enough things in the enough divisor in the linear system of L such that every point sits in such a curve. If you have all these assumptions, magically X becomes semi-stable. Proof is kind of obvious, right? So you take T1 compatible with H1, so you can write, no question. So it's compatible with H1, and then from this you write D1 as A H1 plus gamma. What you do is you throw away this one and continue. So this is exactly as before. You do inversion of adjunction. You go on gamma, and then on gamma restricted, of course, you take D2 to be some, let's say, A1, A2, H2, and so on. Right. You keep going down, and what happens at the end is that this Ln being less than N plus 1 over R, this guarantees that multiplicity at the end is at most 1. So you have your log canonicity at the bottom on the curve, and then you just keep going. and you get what you want. So you see, I mean, it's not a foolproof, right, by no means, but that's the idea. And the corollary of this, so let's see how useful this could be. So for example, you can take just Pn, forget my proof, look at this one, take a hyperplane, you have all these assumptions satisfied. So this was known before. You can also similarly prove any in one or two lines using this. I mean, it's not, you don't even prove it, it's an exercise for the eye. The piezo surfaces of degree at most 3. This was known previously by Tian. They are all K-stable. This is again easy to do. In fact, hypersurfaces in Pn plus 1, they were known by Fujita, but now it's a simple consequence of this. Again, just take minus k itself, the hyperplane, and you get this for free. Similarly, double covers of Pn branched along divisor D of degree at least n plus 1. This was known by work of Derdan. Again, it's a simple corollary of this. Some new stuff you can do here. So P6 in 1, 1, 1, 2, 3. The piezo threefold smooth. This is going to work. And there are many more of this in the paper. We just list them. Maybe some stuff are there. We don't see it, but anyway, it's very easy to do. Cool. Any questions on this? If not, I'm going to really use it like a blackboard. So I'm not going to go to the next page. And I would like to write a quick theorem. I mentioned this before again, so AZ20. So you take xn in Pn plus 1, smooth. It's going to be K-stable. Right. So I'm writing at the top if you didn't notice. So if you take a hypersurface of degree n in Pn plus 1, it's going to be K-stable. That is not going to follow from this. You can try. Proof of this. So as I said, sometimes you could take your choice of E to, you fix a point X first of all, and then you can take E to be around that to contain that point, and you use this freely given induction. That's not going to work here. What you do is you basically do a trick. You make a choice of a divisor away from your point. Right? You go one dimension down, and then you do this induction process as before. And then at the end, again, you do this same trick again. I'm not going to say what this trick is, but you basically what you do, you ensure that at the end, when you land in dimension, say 0, you have 2 points on that curve. So that curve, so that now the degree, if you like, is too big. There are 2 points, and that ensures that you have to be, things have to be like canonical all the way up. So this proof is really involved. It's not as easy as I just said. But what I'm saying is you don't always get things for free. And again, the divisor that computes delta is hard to find. So most of the time we manage to estimate it. So you make a good choice, you experiment, you fail, and then you find the one that by going down, it gives you a nice induction that estimates it. You just want to show that this is at least 1. Anyway, so that is the story there. I'm now going to move to the new part very quickly. Seshadri constant. So suppose L is a, so now for the first line, I'm not assuming anything is Fano. So L is an ample line bundle on X, not necessarily Fano. You define epsilon, you fix a point X. L. Now this is going to be the supremum of lambda bigger than 0, such that pullback minus lambda E is nef. So this is really just your nef threshold. So I is say slope of x and x, right? And E is the exceptional. If you like, the way to calculate it is this is the infimum of C times L multiplicity of C at X. Good. If you don't have this, that's not going to work. So, cool. Anyway, so if you know what it is, you know how to calculate this. I have some stuff to tell you, but I'm going to skip it and write the theorem we had. So, theorem, which is very similar to the previous one, slightly more powerful. So X is Fano, L is an ample line bundle on X, and you take a point, it's a point, and assume as before there exists H1 to H minus 2. So you have n minus 2 members in your linear system, such that their intersection contains the point. And now this thing is going to be an irreducible reduced curve. Of course, complete intersection. Sorry, complete again. Surface. Should I give it a name? Yeah, maybe. Call this S, the surface. Now, if you have all of these things, it's not going to give you that beautiful theorem that this is going to be K-stable. Instead, it bounds your delta. So delta X is going to be at least n plus 1 over volume of L times the Seshadri constant of L restricted to your surface. So you can go all the way down to your surface, and the nef threshold is going to just decide this for you. Right. And the idea is that so the larger epsilon is, by that definition of the top right, you can see the larger epsilon, the milder the singularities of L are. The milder the singularities of L are, the larger delta is going to be. Right. So it's very it's natural, but this inequality is very strong. There are some weaker inequalities known, but they're not going to be very useful. Good. I would like to just quickly, just for fun, I'm not going to prove it, but it's easy to again see what you do. So you find D1 compatible with H1. I'm trying to advertise reading the proof. So that gives you, so you maximize the multiplicity of V along H1, so you get this sort of thing, n plus 1 H1 plus some gamma, right? And from this, you know that gamma is going to be n over n plus 1 L, right? And now you do inversion of adjunction. Again, as before, you get that delta X with respect to L is at least n plus 1 over n delta X of L restricted to H1. What you do is you repeat, right? You repeat. So should I write it? N plus 1 over n, then n over n minus 1, You go 4 over 3, delta X of L restricted to S, right? Which is really n plus 1 over 3 delta X. Now you're at the level of the surface. Now we have a new lemma that says delta X of L. So this is on a surface. Now go down to dimension 2. Everything in this lemma is there. It's going to be at most 3 times L squared times epsilon L. Proof of this is calculus. In fact, if you want to have fun, if you teach calculus, there is a lemma that we use to prove this. It's purely calculus. It's just integration over the real numbers. You can safely use it in a very difficult exam question, for a difficult exam question for undergrad, or if you like a math Olympiad or something. Anyway, so if you plug in these numbers, you get what you wanted. Cool. And the final theorem I would like to write, but not prove. So you take a hypersurface in Pn plus 1, smooth Fano, and index R. So I didn't really define index, but if you like, this is what index is here, is n plus 2 minus d. And as a matter of fact, so simply write the largest number by which minus k is divisible. It's going to be your index. So fix your you don't really need this, right? So this is not a part of the theorem. So you take a smooth Fano of degree d, a hypersurface of degree d in Pn plus 1 of index R. Now, if R is at least 3, so we didn't have this before, and n is at least R cubed, then X is K stable. Right. And now proof of this uses the Seshadri trick. Right. And that inequality of n is at least R cubed is forced by what we know about Seshadri constants of surfaces. This can be improved. Right. This is not a God-given thing. It's just because of the limitations. Let me just say a few words about this theorem. So there is a well-known conjecture within the growing community. It says all smooth Fano hypersurfaces in Pn plus 1 admit Cayley-Einstein metric. It's really hard to verify. So previously known, as I said, so if let's write it HD. So if D is 1, is nothing, it's just Pn. We've seen it several times. If D is 2, then you get a quadric, and this was also known previously, but we gave an algebraic proof 2 for this. If R is 1, so now I go top, right? The highest degree you can possibly have. This was Fujita, but you also saw that it follows from the theorem we had. R equal to 2. This was AZ20 that we saw a few pages ago. The only other thing known was if you take a cubic fourfold. So this was known by a paper of Liu in 20. Right. So these are case statements. Right. Nothing else was known with index larger than 2, except the trivial cases of degree 1 and 2. So there are lots of things here to do. There are lots of gaps. The gap is massive. So projects for people. Thanks a lot.